Hey everyone, back again with another video. This time we're going to be looking at calculating pi, the irrational number pi, with CUDA, and we're going to be using the Monti Carlo method. Okay, so we're in our usual directory here, so I made a directory called Monti Carlo, I think. Okay, so again, I've already created the files like usual, and I have the code actually commented out in each one, but I'm gonna go through them like as if I was doing them on the fly. Okay, so we're gonna have our main file, and let's just go over what we're doing here. So I brought up the Wikipedia page. Basically calculating the Monte Carlo method, there's a nice simulate or animation here. And what we're doing is looking at basically a quarter of a circle, generating random numbers, and basically determining the ratio of the numbers that land within the circle versus to the ratio of the numbers that are in the circle to out of the circle, and that'll give us a quarter pi. Then we multiply by 4 and we can get pi. So if you need to just read through this, it's a really easy example. It's not hard to understand if you've never done this before. Okay, so let's get started again with our main file. What do we normally do here? Let's get our includes in. We'll use the IO stream. So as you can see, we're going to be creating a kernel file, so I'll include that now. And I'm going to be using a bunch of other things as well. Time. We need to be able to generate some random numbers. Actually, I like to have all mine. Yeah, just my pet peeve. Okay. And we also need another include here. We haven't used this before. This is using CURAND, which is the CUDA random generator. So that's, I believe it's just called, maybe that. Let's check. Again, I already have the code finished here. Yeah, CURAND. I think we need math. Okay. So we create our main function. Let's go through the steps. So what do we need to do here? We need, we're going to need basically an integer on the host and the GPU to store basically the count. So the number of times a random number lies within the circle. So the number of times we get a point within this core of a circle, for example. So we'll call that count, one for the host. Oh, again, that is back. That's annoying. One for the host. One for the device. And then we're going to need just a variable pi. It's going to be a float. And we'll need the number of times we're going to be running. The number of times we're going to be generating a random number to do this Monte Carlo simulation. So we'll just stick with that for now. We can change that later. Allocating memory. So it's going to be the host. Using a malloc. I think for the next one, now that we've got a little bit of time here, I think the next one I'm going to be doing is actually, the next video will be on generating prime numbers with CUDA. It's a pretty cool example, I think. using the sieve of Eratosthenes, I think it is. Nope. Oh yeah, we have to use our boolean here. What else do we need to do? Don't need to do any copying. We're going to have two kernels actually that we haven't written yet. One's going to be, we'll call it the setup kernel, and then the Monti Carlo kernel. The setup kernel is just going to basically, it uses CUDA to set up the random number generator on the GPU. What else do we need now? So once we've done that, we're going to copy results back to the host, display results and timings for GPU, and we'll have a serial version again. That doesn't serial, just to compare timing results, and then delete memory. So we can do that now. This part's easy. We need to delete our host. Delete our device count. Why am I saying point as count? Did I do that anywhere else? No. Okay. And so we're going to need actually one more, and that is this thing called CUDA state. And it's going to be a device pointer. This is to use the CUDA random number generator. So we'll also delete that later. Okay. Setup kernel. So we're going to do grid size. Just to start off, we'll just do 32. Block size would be also 32 threads per block, 32 blocks as well. And then setup kernel, which we haven't written yet, but we will. This is going to take our D state, and that is it. And then Monti Carlo kernel. And what's this going to take? It's going to take the D state. It's going to take our count. And it's just going to take, it's going to take an additional integer, and I'll actually write that up here. For now, we'll just call it M for lack of a better word, and we'll just say 100 for now. I'll explain what this does in a second. Okay, copy results back to the host. So the thing that's on the device is the count. The total count of the number of times the random number lies inside that quarter circle. So we need to copy that back. So we're going from the destination here is going to be the host. Source is the device. It's just an integer, and CUDA, and copy device to host. and display results. Right. Okay, so when we copy this count back to the host, remember that only is a count for the quarter circle. So what we want to do actually is it's going to be the count times 4, and that'll be the number of points that would lie within the whole circle, not just the quarter circle, and then we want to divide by the total number of points that we attempted to do, which will be m times n. And I'll explain what m is in a couple of minutes. And this will give us our approximation to pi. Okay. Okay. And then let's write the serial version. This is easy. Okay, so what do we need here? We're gonna do a for loop. From I 0 to n minus 1. Inside that we will have temp, an additional while loop, so basically I'll explain the m here now. For the serial version we're going to be running this Monte Carlo method n times, and for each n we'll run an additional m times, so we're running a total of n times m. Now in the serial version, you might just think that why don't we just do that and skip the inner while loop, and we could do that, but I'm kind of keeping it in line with what we're going to be doing on the GPU, which is to sort of do some additional calculations that take advantage of shared memory, and so it'll make sense of it. And then what do we need? Oh yes, we also need to set up our random number generators for the CPU version, which is different than the cuRAND, or you can use cuRAND to do it for the CPU, but we're not going to. And I'm just going to cheat here and look at what I've already written, and it's actually going to be this section here, because I always forget this. So this is just these two lines here, default random engine and uniform real distribution, just set up the random number generator for our CPU version. So it's going to be generating uniform random numbers between 0 and 1. Okay. And let's continue. Now, how do I call this again? Distribution generator. Shall I just copy this here? Okay. So what do we do for each run? Each number, the random number we're generating in this Monte Carlo method, we create an x, a y. Both these x and y's are uniform random numbers between 0 and 1. Calculate what the radius, well, x squared plus y squared equals basically an r squared, and then we figure, is this within the unit circle? If it is, we increment the count. If it's not, we don't increment. And then regardless, we increment the temp variable just to move through these m times. Okay, and I think that's it. And then I also have the clock here for timing results. Clock TV. And of course we need to, so in this case for the serial version, it's just pi is equal to our count times 4. Remember, the count is the number of times the random number is within the quarter circle, so we need to multiply by 4 divided by n times n. Okay. So I think that's good for the main files for now. Let's write our kernels. So if not defined, kernels h. Okay. So we're going to have 2 kernels. Setup kernel that takes a QRAN state pointer, and of course I need a void here. And then our Monti Carlo kernel. This again takes the QRAN state. Takes an integer pointer for our count, and it takes an m, again this extra integer. Okay, that looks good. The kernels, let's copy this. I think that's all. Oh yes, we also need, yeah, we need this as well. Okay. Actually, what we'll do is we need to move this into here. Okay. Okay. Now I'm just gonna copy out this state. It's a very short kernel. It's just this. Explain what this does. Stupid circle, that's really annoying. So that's it. It's just to set up our random number generator for on the GPU. Just have our index, and then first argument here is just a random seed. You can choose any number for that, and then to make sure that each thread has its own random number and they're not going to be correlated, we put the index here, so each thread kind of changes how this number random generator is going to work. And then our state is what's holding these random numbers for each thread. So we have one state for each thread, for example. Okay. And let's now continue with the main actual kernel that's interesting. So what do we need? So we're going to actually use some shared memory here, and this will explain what that m was for. It's an int, a cache. We'll just hard code it to be the 32, one entry for each thread, so right now we have it as 32 threads. We can change that later. And we'll make sure initially it's 0. each thread, and sync. So what we're basically going to do is we have, for example, we have 32 blocks. Each block has 32 threads. And then each thread, in addition to that, is going to be running m times. So while temp plus an n, and then this is basically like the serial code, except the only difference is, let's just copy this out. Let's see what the only difference is, okay. So we have float x, and obviously this changes, and this will change. How do we call our random number generator on the GPU? It's qrand uniform state index. So this for index or for thread index, we get a random numerator. Do the same thing here. Okay, looks good. Still do that, need that. And what do we actually, okay, so here's the difference. Do we need a separate variable? What did I call this down here? Oh yeah, right, using our cache. So here, instead we're going to increment the cache for that thread. The thread's corresponding entry in the cache. So what this means is basically each thread is running this in parallel, this section here. Each thread is running this in parallel, and it's updating its entry in the cache. So we're going to have this cache of 32, almost like 32 counts. And then we need to kind of combine all those back using a reduction like we did in the last tutorial. So basically, let's do that. So yeah, okay, let's see if I can remember how to do this. Okay, without cheating. Okay, what do I need? I need inside int. Let's just call it I. This block down. While I is not 0, this is a reduction. If thread idx dot x is less than I think cache thread dot x is plus equal to cache, yes, plus I. So this is reducing these 32 entries in the cache down to the first entry. So then we only have to deal with cache bracket, 0 bracket. What else do we need? An I divided by 2 and a sync threads. And then this is basically just the last part here is an update to global variable count. Okay, in this case this is actually a little bit easier than the last tutorial where we did the finding the max entry in an array, because this time we can actually use atomics instead of having to use the mutex idea. So what we do here is only the first thread is going to do this. It's going to do an atomic add. and it is adding to our count and cache. It's adding cache 0. Okay, I think we're good here. Let's just cheat and double check what I've got. Yeah, that's right. Yeah, I think we're okay. I should do this as an int. I don't think it matters, but okay. Oh wait, yeah, and I forgot. We have our usual makefile. I don't think anything has changed here from the last tutorial where we did the finding the max value in an array. We called the files the same, so nothing changes there. Okay, let's go back to here and recap what we have. Okay, 32 blocks, 32 threads each. Okay, that's good. Allocate our memory. Ooh, one more thing. We do want to make sure that the initial count is set to 0. Otherwise it gives you some random number. So we're going to use the CUDA mem set for that. I don't think we've used this before actually. Device count. Set it to 0. Size of int. Okay. Good. Yep, that should be fine. That should be fine. Copying the count back to the host. Pi is then equal to 4 times that count divided by the total number of random simulations, which is m times m. Yes. I think this is good. Let's try and compile. This is always the risky part of that. Let's see if this works one try. Usually it doesn't. Okay, make. Nope. Of course, it's an easy fix. What is it? Is it time.h? Time.h. Oh man, this circle thing, I gotta figure that out. Oh, let's try again. $29 and 57. D state. Why is that complaining? What's the 57 line? We forgot to add that in. That's part of it. 64. Yep, we need that. Why is that upset? Oh, obviously. Yeah, we need to do a CUDA malloc for the D state as well, just like any other variable. And what is this going to be? We basically need one for each thread, so it should be n size of command state. Is it? Yeah, each thread needs one. Yeah, so it's this 32 times 32. Our n is our total number of threads. So yeah, okay. And I did delete that. Okay, let's see if it works. Okay. Let's 29 there. Let's check that out. It's a warning. 25. Oops. Oh, we do need to set that to 0. Okay, we'll compile. Let's risk running. Yeah, I think it's working. Okay, so the approximate pi calculated on the GPU, 3.1448. So for those of you who don't know pi, the irrational number is 3.14159265. So that is an approximation. Looks like it's working. CPU, same thing. Looks like it's working. Obviously, the numbers are different slightly because we're using different random numbers for each time. Okay, so let's just, the only thing left to do I think is add timing results and just play around with this. Okay, and for the timing stuff, to speed this up, I'm just gonna copy it because it's the same as last time. So let's actually add a setup timing stuff. Okay. Run the kernels, and then it's just after the copy we'll do this. And then we can report our results as well here. Okay. Approximate pi calculated on GPU is pi. And took that's and took GPU elapsed time. Okay, and then down here, same thing. And we do have to remember it is, what is it? It's 1,000 times this. God dang it. Let's just paste that. Okay, let's see if this works. No, what? 56, I screwed something up. Yep, right there. Okay, looks like it's compiling. Let's try and run it. Okay, let's review this. So again, we got our, actually I'm gonna fix one thing that's gonna bother me. Right, just add a space in there. Okay, running. Okay, so we got our approximation of pi, and it tells us that it took 3.5 milliseconds. This is in milliseconds, by the way. And the CPU took 1 millisecond. So you're probably asking, well, why the heck would I use the GPU then? Well, let's remember we're only doing 32 by 32 threads. That's not that much. It's like 1,000. So let's instead do 256. 256. So because I'm bad at math, let's see how much is that. 256 times 256. Yeah, 65,000 threads running, and then each of those threads is running 100 times. So let's try that. Oh yes, and let's not forget we need to change, we've hard-coded this, so let's change that. So basically what we're doing then is, so 256 times 256 is 65,000 times 100, so we're doing 100 extra for each thread. So let's see the timing results for this is 6.5 million, just over. 6.5 million different Monte Carlo simulations or runs of this code to find pi. Okay, so already, oh, something went wrong because that's reporting the wrong pi. Oh yeah, so gotta do this too. Let's do that again. Okay, again we get an approximation of pi, and this time it's more accurate. You'll notice it's 3.141, so we're getting there, it's getting closer. Okay, so now already things are starting to even out. Still the GPU is taking a little bit longer, but let's up the ante a bit here. What if we do a really big simulation? So let's keep the 256 by 256, but let's do times 1,000. So what is this? This is 256 times 256 times 1,000. Should be able to do that. In my head, yeah, 65 million. So now we're up to 65 million different simulations. Let's try that. Okay, running it. Now you can definitely, right there you could tell. So we have our approximation of pi. And now you can see here 123 milliseconds to 978, so it's now the GPU is faster. What if we, let's keep going. Let's go crazy on this. 20,000. So this is what, times 20 times bigger than that. 1.3 billion simulations. Let's see what we get. Yeah, this is going to be pretty big, I think. GPU reports pretty quickly, okay. 316 milliseconds. And the CPU is still running. And still running. Still running. There we go. So now you see the big difference here. 316 milliseconds to almost 18,000 for the CPU. So that's almost 18 seconds versus a third of a second. So clearly the GPU here is showing its potential, usefulness as increasing performance. Is anything else? Yeah, so I think that about wraps that up. This was just a quick one. I think it's a pretty cool, interesting example. I think the next time we're going to do, I want to do one more simple example with CUDA, and that one's going to probably be maybe writing a prime number generator or something like that, basically listing, the first n primes, where n is a big number. Probably going to use something use maybe the sieving techniques of, I think it's called the sieve of Eratosthenes. So maybe write something like that, and then after that I think we'll do some more complicated ones with CUDA, maybe using binary trees and that kind of thing. Anyways, hope you guys enjoyed this somewhat quick tutorial, and thanks for watching. Bye.